Real quick review with our acid and base definitions and when to apply them. Our Bronsted-Lowry definition is looking at the transfer of protons, also known as our hydrogen ions, so the transfer of H+. So look at the reactants and the products and look for that difference. If the only thing that's different is the location of a hydrogen atom, a single hydrogen atom, then you're running under that Bronsted-Lowry definition for a reaction. All right? Remember, that definition is too narrow. So that's where Lewis came in and said, let's expand that definition out to electrons. So the Lewis definition now applies to all reactions, Bronsted-Lowry or not. Every single reaction you can possibly imagine, Lewis works. That's an overstatement, but it's close enough. Okay? When we're looking at our Lewis, we're still running under those same kind of premises, so you can pick a standard acid, say HCl, and if it's going to act as an acid, yes, it donates that H+, but at the same time, what does it need to accept? Electrons. Okay, so we can get the definition of our Lewis acid coming from our electron acceptor, even using the Bronsted-Lowry definition. The next two definitions that come out of our acid-base reactions are nucleophiles and electrophiles. Those ultimately refer to the transfer of electrons, or the motion of electrons, which is effectively the same thing as Lewis. There's one slight caveat to that. Your nucleophiles and electrophiles are looking at the transfer of electrons, okay, where you're not reacting hydrogen. So that's our electrophile-nucleophile definition. Our Bronsted-Lowry, we're looking at transferring hydrogen ion. And Lewis does what? I guess I should circle a little higher. Our Lewis definition is everything. So every reaction should have a Lewis acid or a Lewis base. Right, within that, we can subcategorize and either look at it as a Bronsted-Lowry acid-base reaction or an electrophile-nucleophile reaction. Okay? So that should help a little bit with those definitions. Remember, I will test you directly on these definitions during probably the first exam, and then you'll start seeing application questions for every other exam. Okay? So let's take a look at an application question. These are the primary functional groups that you will be using this semester. Okay? So what I want you to go through and do is look at each of these functional groups and classify them according to our Bronsted-Lowry acid-base definitions, or our Lewis acid-base definitions, or our nucleophile electrophiles. Okay, so we'll do about 2 or 3 minutes looking at these. So pick a functional group, start to evaluate what possibilities it has, and then just list what those things are. Okay, talk to the people around you if you've got questions. You can also raise your hand, and I'll come around and try and guide you through a few of those as well. Yes, look at those hydrogens, those beautiful hydrogens attached to it. Okay. Yes, we do have hydrogens. Are those going to be good Bronsted-Lowry acid hydrogens? No. Why not? The difference in electronegativity between the hydrogen and the carbon is so small, which means what charge builds on the hydrogen or the carbon? Zero. No charge. For it to act as a Bronsted-Lowry acid, what does it have to give off? H+. Do we have something that's remotely H+? No. Right? So those hydrogens aren't going to act very well as a Bronsted-Lowry acid. So our alkanes, we eliminated one of our 6 possible definitions. How would it act as a Bronsted-Lowry base? What does it need to be able to do? It has to accept hydrogen ions. That's difficult if we don't see those hydrogen ions. To accept those hydrogen ions, what does that carbon need to have? Electrons. Do we see available electrons to react with a hydrogen ion? No. No. What does that mean? It's not a Bronsted-Lowry base. Okay. How about a Lewis acid or a Lewis base? Yes. Okay. To be a Lewis acid, we have to be able to accept electrons. If we take a look at CH4, for it to accept electrons, we need to have something that's partially positive. Is there anything partially positive in CH4? No. Can it accept electrons? No. Is it a Lewis acid? No. No. How about a Lewis base? What does a Lewis base need to be able to do? Donate electrons. Do we have electrons? No. So it can't be a Lewis acid, Lewis base. If we started with that, that means it can't be Bronsted and it can't be our nucleophiles or electrophiles. So what reactivity do we get for alkanes? Fat load of nothing. Okay? So the reactivity of our alkanes, as we'll talk about a little bit later today, is ultimately nothing. They're very difficult to get to react. Okay? Are they strictly non-reactive? No, we can force them to react in a variety of circumstances. You've already done one probably multiple times. Anybody had a fire anywhere? Lit a fire? What are you burning? What are you doing in that process? You are reacting oxygen with some kind of carbon structure. Okay? If you look at standard lighters, what's the fuel that they're using? Butane. Remember that A-N-E ending, if you think back to when we briefly talked about nomenclature, is referring to an alkane. We are doing a reaction when we combust alkanes. We are changing the structure. Okay, why do we typically not look at that as a valid organic synthesis method? We end up converting our carbon chain into CO2. CO2 is incredibly stable, and we really can't do a whole lot with CO2, which is also why that's a massive environmental problem. Because when we combust our alkanes, we generate that CO2, and we can't do anything with it. We can't react and reverse that reaction back to something useful. So instead, we generate CO2 that goes off into the atmosphere and potentially increases temperatures, and we get global warming. Okay? So kind of an interesting process. What happens when we move to the alkyl halides? Okay, so we do have electrons on the chlorine. Good call. I went through and put them on the other one, but forgot to put it on the chlorine. So where do we want to start? Which definition do we want to work with first? Okay, Lewis definition probably makes the most sense to start with that, because once we have Lewis, then we can decide if we have Bronsted or if we have a nucleophile electrophile. Okay, so I heard Lewis base. Okay, to be a Lewis base, what do we need to have? Electrons. Where are there electrons? On the chlorine. Cool. So far, everything seems to match. For that chlorine to act as a Lewis base, we have to take those electrons and share them with something else. How many bonds would that chlorine have? 2. How many bonds do our halogens have? 1. Can the chlorine act as a Lewis base? No. It's a pretty horrible Lewis base. It does not want to share that extra pair of electrons. Okay? So just because we have a source of electrons doesn't mean that those electrons are reactive. Okay? Just because we have electrons does not mean they are reactive. The chlorine, while it does have that pair of electrons, cannot share that pair because it ends up going to a larger bond structure than it can sustain. Our halogens hold 1 bond. Okay. Is that always true? No. If you think back to probably your Gen Chem Lewis structures, they probably showed you a few cases where your halogens can have more than 1 bond. Okay. Those are very rare exceptions. Okay, so when we think about our halogens, it is 1 bond and 1 bond alone. That chlorine cannot share its electrons. No Lewis base. Okay. Well, Lewis has 2 definitions, Lewis base and Lewis acid. Okay. Could this structure act as a Lewis acid? Where could it accept electrons? To accept electrons, what charge do we need to find in the structure? A partial or a positive. Do we have a formal positive? Yes. Not a formal positive, but we do have a partial positive. Where's that partial positive? On the carbon. Why is that carbon partially positive? The chlorine being more electronegative is withdrawing that electron density, and our carbon becomes partially positive. Right? What does that do for us? Well, now what I can do is bring in a source of electrons, let's just call them electrons, E, and those electrons can share with that carbon. Anybody see a problem with that? It's already got its octet, so if we share 2 more electrons, carbon has too many electrons. Is there a way that we can shuttle electrons away from that carbon at the same time? do we have, say, a weak polar bond? We can take the electrons in that carbon-chlorine bond and put them directly on the chlorine. So our carbon acted as an Lewis acid. It accepted electrons from our electron source. Yes, the structure rearranged. It changed its chemical composition. But when we go through and do a reaction, what would we expect to happen? It's going to change its chemical composition. Okay? So when we look at our alkyl halides, a really good definition for them is Lewis acids. That carbon is a Lewis acid. It can accept electrons. It may not be the greatest. Why is it not the greatest? To be a really good Lewis acid, what would we expect to see? A formal positive charge. We only have a partial positive, so it's not the greatest, but it's a pretty solid Lewis acid. Okay? Can it be a Bronsted-Lowry acid? No. Okay, we'd have to look for that hydrogen. Do we have a partially positive hydrogen? The hydrogens are all connected to the carbon. That bond is nonpolar covalent. We don't have partial positive hydrogens. No Bronsted-Lowry acid. Right? If we have a Lewis acid but not Bronsted-Lowry, what's the other definition that fits? We now have an I can't spell. It's all sorts of weird. We have an electrophile. Okay? No transfer of hydrogens. Yeah?
So would the carbon then have 3 hydrogens in a lone pair, and then the chlorine?
Carbon does not pick up the lone pair. For it to be a lone pair, it would then be negatively charged. An electrophile means it's accepting electrons. I think I know what you're saying. In the end of this reaction, are we saying that this is the result? No. Anybody know why?
We're saying the Cl was replaced with something else.
So a couple things go along with that. So our Cl would come off. There's our negative. I know I was a bit fast and sloppy. What I drew here was just a source of electrons. That source of electrons must be attached to an atom. Why does it have to be attached to an atom?
We need a bond coming off of the carbon.
Nope.
Well, it's a pair, right?
How stable are electrons? Not stable. How often do we see electrons sitting on their own?
We never see electrons.
Never on their own. Okay? They are always attached to something. You think even with our electrical current, okay, the electrons aren't just sitting in there. They're sitting on atoms. They're sitting on metal atoms. When we open that circuit, we allow for the flow of the electrons to jump from atom to atom to atom. They aren't just free-floating electrons off on their own. We never, ever, ever have that. Okay? They must be attached to an atom. Okay? Questions? It's a good one. What happens when we move to the alkenes? These are a little bit trickier. What do you see with the alkenes? What's special about the pi bond? We've got too many electrons in that space. We can take that pi electron system and put it out into a hybrid orbital. So our alkene can act as an electron donor, which means it would be a Lewis base. What if it shared those electrons with a hydrogen? What would it be? It would be a Bronsted-Lowry base. Could it share those electrons with something other than a hydrogen? Be a Bronsted-Lowry base? Just in case that's what the face was about. Okay. It could share them with something other than a hydrogen. Could share them with, say, something like a boron, which we do end up seeing. Okay. If it's shared with something other than hydrogen, what do we have? We have a nucleophile. So our alkenes can act as Lewis bases, Bronsted-Lowry bases, and nucleophiles. All three are possibles, depending on what you're going to react them with. Yes?
Is it not a nucleophile if it's shared with the hydrogen?
If we now add a reactant, and that reactant is a hydrogen ion, does our alkene act as a nucleophile? No. Then it's acting as a Bronsted-Lowry base. So until we specify what it's reacting with, all definitions are possible. What do you think about the pi bond? Or sorry, not the pi bond. The alkynes.
We have 2 pi bonds to share.
We have 2 pi bonds. Right? So ultimately, we get the same results as we would get for the alkene, which we'll end up seeing when we talk about the reactivity of alkenes and alkynes. Their reactivity is very, very similar. There's one extra little chemistry that comes from our alkynes that we got to watch out for. Our alkynes can also act as Bronsted-Lowry acids, which I guess then also technically means Lewis acid. How does that work? That's still just a carbon-hydrogen bond. Why is that hydrogen positive?
Electronegative? There's a dipole.
Why is it more electronegative, and why does the triple bond matter?
Triple bond sucking up the electron density.
Not quite. What happens to the hybridization of that carbon? Becomes sp. That increases the electronegativity. What we're actually generating in this case is now a very weak partial positive on that hydrogen and a very weak partial negative on that carbon. It's not super acidic, but it is much more acidic than the alkane and the alkenes. All right? Alcohols, I'm not even sure I really want to look at the alcohols because they're a mess. Why are they a mess? Which of our 6 definitions work for alcohols? All 6. Every single one of our Bronsted-Lowry, Lewis acid base, and nucleophile electrophile works for an alcohol. Right? So you should be able to go through and identify all the partial charges and then evaluate how each of those could potentially interact. Right? And you should see that all of those are possible reactions. Okay? Which is why everybody hates the alcohol chapter. Right? Because you get a billion different things can happen to it. Questions? Okay. So this is ultimately just to get us in the mindset of looking for those reactivities, looking for our acid-base characteristics. When we start looking at reactivity, which will actually be after spring break, we're going to be coming back to these definitions and looking at each of these functional groups and how each of them can interact and react. Okay? So, if there aren't any questions, we'll move into chapter 4. Sorry, yes.
The one with the alkene.
Yes.
You said it could be a Lewis acid and a Bronsted-Lowry acid, but it won't be an electrophile.
Alkene was Lewis base. The alkenes were not a Lewis acid. Maybe the alkyne? Is that what you're talking about?
I'm sorry, alkynes.
The alkynes, the new chemistry is a Bronsted-Lowry acid because of that acidic hydrogen.
Right.
Okay. Which then, by definition, means it's a Lewis acid. It won't be an electrophile
Be an electrophile
because what's the positive atom?
because it's the hydrogen.
It's the hydrogen that's positive. So we don't see our alkynes acting as electrophiles. Okay? So, chapter 4, we're getting a lot of nomenclature, which I'm going to try my best to kind of just skim over, because ultimately when it comes to nomenclature, I am not your best resource by far. Okay? But I'll try and get you kind of the bare basics of that. Where I will be much better suited for you is talking about kind of the brief properties that we might expect from our alkanes. So I guess that would have been an important thing to mention there. This is our alkane chapter. And then we're going to start looking at how we draw structures. So while chapter 4 is officially the new introduction of a new functional group, our alkanes, we're really going to start to push how we draw our three-dimensional structures and how we can manipulate those three-dimensional structures. Chapter 5 then takes that a step further. Right, and says not only how do you draw these on paper, but then what's the relationship between those drawings, right, which becomes even trickier to understand and manipulate. Both of these chapters, I highly, highly encourage that you bring a model kit for. Right, it's going to be really important and helpful to go through and deal with model kits. Right. I've got one up here mainly because I forgot to grab more. Depending on how far we get into chapter 4, we may take a look at those. Right. To encourage the use of model kits, anybody know how I'm going to encourage that? You can use a model kit on the exam. One of the fun things with model kits is you now don't have to think about the structure in 3 dimensions. You build it, look at it, there's your answer. Done. There isn't, oh, I got to flip it, rotate it, spin it, stand on its head, there it is. No. You just look at it, there it is. Draw what you see. Okay, it's a lot easier to deal with. You will sort of have time to use model kits on the exam. The sort of comes from how you come into the exam prepared. If you come in with just a box full of atoms, no, you will not have time to use model kits on the exam. If you instead come in with a very particular structure that maximizes your efficiency of what possible questions could be asked, yes, it becomes exceedingly helpful. So it might be nice to know what structure to bring in. I'll tell you. Okay. For those of you that are really planning ahead, it's methyl cyclohexane. That's the one you'd end up wanting to use. Okay. So chapter 5 really gets into making things look weird. Again, really helpful for a model kit. Your exam is in 2 weeks, I believe. Next week's lab is a model kit lab to, again, encourage you to use model kits, because it's these 2 chapters that are massively important when it comes to models. Okay? After these 2 chapters, you're probably okay to kind of ignore model kits for the rest of your life, potentially. Okay? Questions? I know that was just the title slide. Let's actually make it more interesting. Okay. Alkanes are hydrocarbons. Hydrocarbons is ultimately what we're studying in organic chemistry. It's any structure that has carbon and hydrogen within it. It's a little bit weird, or more strict definitions beyond that. But our alkanes are the simplest form of our hydrocarbons. So very minimal reactivity. We're looking at sp3 hybridization around each of our carbons, all single bonds. Okay? Nothing really fancy going on with them. If you draw out a bunch of different alkanes, say start with 1 carbon, then 2 carbons, 3 carbons, 4 carbons, 5 carbons, however many carbons you want to put in there, and then put in the hydrogens around it. What you'll notice is that there's a pattern that moves along with that. Right? If we start with n number of carbons, the number of hydrogens that we'll need to go into that structure will be twice that number plus 2. I know that sounds a bit weird, so we could take a look at our formula for our first alkane. Okay, how many carbons do we have in that structure? 2. How many hydrogens? Okay. If we match up our formula, what's n? 2. What's 2 times n? 4 plus 2 gives us 6. Our formula matches. What if we looked at a propane? And I'm going to give you the condensed formula. Propane gives us 3 carbons, so we'd have C3H. Oh, yeah, you did add that right. Sorry. C3H8. Okay. If we go through and again go back to the general formula for our alkanes, N is 3. 3 times 2, 6 plus 2, 8. There's our alkane. Okay. So straight chain alkanes or even branched alkanes will always hold this formula. It is always true. What happens when we move up to an alkene? We assume that that alkene had hydrogens around it. We'd have C2H4. That doesn't match our alkane pattern. Go figure, it's not an alkane. Okay. How many hydrogens did it lose? 2. Okay. Where did those 2 hydrogens go? They went to making the pi bond. So every pi bond results in the loss of 2 hydrogens. So when we move up to the alkyne, what happens? We lose 2 more. And our formula again changes and we get C2H2. So what would we expect our formula should be for our aromatics? I see 3 bonds, so we got C6, see 3 pi bonds. We lose 2 from each, so if that was a saturated alkane, we might say that that was going to be C6H. Probably predict 14, okay? Because 6 times 2 plus 2, we might say 14. With 3 pi bonds, we should lose how many hydrogens? 6, so we would expect the amount of electrons to be. How many hydrogens are in that structure? 6. Look at each carbon. How many bonds are shown to that now red carbon? 3, which means there's 1 implied hydrogen. There are only 6 hydrogens on this structure. Why does it not match the formula appropriately?
Because of aromatic.
There's not,
Nope.
There's not any carbon, there's
shape.
3 hydrogens.
It has to do with the end carbon. We lose 2 hydrogens for every pi bond. We also lose 2 hydrogens for every ring. So we can have a cycloalkane. The cycloalkanes will also lose 2 hydrogens. Okay, even though they are alkanes, but it's that extra cyclo addition to it. So when we go through and take a look at our aromatic structure at the end, it's 3 pi bonds and 1 ring. So that's a loss of 8 hydrogens. 14 minus 8. There's our 6. Okay. We will come back to this formula patterning, particularly when we talk about mass spec. Not a huge issue to think about now. I just want to make sure you're aware of it. So every time we've got a pi bond, we lose 2 hydrogens. That's also referred to as 1 degree of unsaturation. So how many degrees of unsaturation would 2 pi bonds be? 2 degrees. And our last structure, that aromatic structure, how many degrees of unsaturation are there? 4 degrees. Okay, because we lost 8 hydrogens. Okay? In general, properties. When we look at our alkanes, we're looking at nonpolar covalent bonds. What intermolecular forces do we get from nonpolar covalent bonds? London dispersion. How strong are those? Incredibly weak. So what do we expect for melting points and boiling points? Very low. What would we expect for water solubility? Also very low. Okay? We can look to our structure and how we put these things together. There are a variety of ways to look at your formula versus your structure. So first off, don't ever give me a formula. Right? And I will try my best to never give you a formula as well, because your formulas really don't mean much. Okay? So you want to convert those into some kind of structure. Those can be Lewis structures. We can do the condensed. We can do a Vesper, and we could potentially do a line angle. Which one we use is dependent on what we're trying to manipulate and what we want to use. Okay, or what we were trying to show with that reaction. Okay? So, if we move to butanes, I know our projectors are all sorts of weird, but this is butane, C4H10. Okay, you notice I listed it as butanes. Why not just butane? So, you're saying I'm a jerk? What was that? Go ahead and draw out the structure for butane. C4H10. Okay, so give me a Lewis structure for C4H10. See how creative you guys can get with this. How do you connect all the carbons in a straight line? Okay, so 3 of you did it. Good. So we could connect them all 3 in a straight line. What we'd be drawing then is strictly the Lewis structure. We might also draw it as a diagonal line or a jagged line. Why would we draw the jagged line like that? As opposed to listing it as...
Each point is a carbon.
Each point is a carbon, so I have simplified it, so I can go through and add in those carbons, and I still come back to the same question. Why would I draw it with the jagged line as opposed to the straight line?
Because it's actual structure.
Kind of, sort of. Do you want to give me... Going back, the structure of the actual model, or the molecule. If we look at a model of butane, you'll notice that we get this jagged line to it. So what we're going to try and draw is most accurately reflect that 3-dimensional structure as possible. The bond angle in that is 109.5. If we draw it as a straight line, it looks like we're drawing it as 180. All right, so what we're trying to do is, again, reflect the actual 3-dimensional structure as best as possible. Anybody come up with a different structure? Yeah? Oh, there's another structure. We've got 2 possible structures that we could have come up for this. Both of these match the formula C4H10. Does everybody agree with that? If you don't agree with me, that's fine.
Yeah.
Takes a little bit of practice to see this. If we take a look at our topmost carbon, how many bonds are shown? 1, which means 3 hydrogens. So we could do the same to the other carbons. Okay, and this is where most people make a mistake. You look at this and you say it's C3H9. That doesn't match.
No, there's a hydrogen on the middle carbon.
Watch out for your middle carbon. Also has a hydrogen. Okay, so these two structures have the exact same formula. Okay, so that's a bit problematic. If we use the same formula, we now get two different structures in this case. Turns out those two compounds also have relatively different different physical properties, depending on that shape. Okay, so what we want to do is always draw out our structures instead of going through and looking at our formulas.
Are these called different things, or are they both called?
So if they're both C4H10, it might be nice to refer to them as something different from the other one. Because if we called them both butane, we're going to be very confused at which one we're looking at. So we definitely need to come up with a nomenclature system, a way to actually name them differently. So this is where we're getting nomenclature from. But then if we don't even want to bother with the name, can we define a relationship between these? Okay, are they the same? No. Are they different?
Same formula. Different structure.
They're the same but different. I like that answer. Okay. According to a chemist, these are not different structures. Okay. They're also not the same. So what we're going to end up introducing is very carefully separating out where we define same versus different versus other issues. If we're going to refer to two structures as being different, their formulas are different. Both of these have the exact same formula, so they are technically not different from each other. We could then go through and look at identical. In the case of identical, the formulas are the same and the structures are superposable or superimposable. What does that mean? We can take the structures and shift them over the top and everything exactly overlaps. Okay, what's the difference between superposable and superimposable? If you don't know, don't feel bad. It took me longer than I care to admit to actually look it up.
They can go on top of each other and be identical.
So, and I don't remember which one's which. Superposable, I believe, means that you can overlay them and you can still see two separate structures, okay, but they all line up. Superimposable means you completely overlap them where you only see one structure. As far as we're concerned, we're going to treat them interchangeably, okay? That there is no difference between those structures.
So superposable is when you take two structures, stick them on top of each other, and you can still tell the difference.
You can still tell that there's two structures, so we never directly overlap them. Superposable means we actually physically take each of the carbon atoms and mash them into the exact same position. They're occupying the exact same space. Okay? Very, very odd nuance of it. Don't worry too much about it. Ultimately, what we're saying is we can't overlap these structures. There's no way I can spin, flip, or rotate either of those structures to get them to directly overlap. Okay? So that means they can't be identical because they are not superimposable. So that puts us into a new definition. That new definition is isomers. Okay? They will have the same molecular formula, but the structures will not be superimposable. Okay? Is that where it ends? No, but that's where Chapter 5 really picks up. So what we can do is take a look at classifying a pair of molecules. So this is before we even get into nomenclature. So given any two structures, I should be able to identify what their relationship is. Okay, so let's take a look at the top two. What's the relationship between those two?
Is that this one too?
That's exactly what's drawn up here. Do they have the same molecular formula? Yes. So, following from our flow chart, we ask the question, yes. So we're now at our A and B again. The next question, are they superimposable?
No.
What's my name?
Mike.
How about now?
Mike.
What can single bonds do? They can freely rotate. I can rotate about, I believe it's that bond, to get those carbons to all go into a nice jagged line. Those structures are indeed superimposable. which means the relationship between those two structures is identical. How many of you could see that? Good. Okay.
The other pairs.
That's why I drew the line up top.
I'm looking at
Well,
this
yeah,
one, that's
if
in
you
the
look at the
black.
screen.
Well, that's your problem, not my problem.
My bad.
We'll come back to those two in a second, too. So if we take a look at those top two structures, can everybody see that those are indeed identical?
Yes.
Or could see that initially? If you can't, which I would actually guess is going to be roughly 70% of the class, can't see that immediately, this is why we have model kits. Okay? The model kits will naturally rotate and spin on their own if they have the ability. So you could build two models to look exactly like these drawings and then start to flip each of those until they are overlappable. Okay? So that's why our model kits can help out. What happens now? Just decided to add that accent there just for the heck of it. These two, go through and call that blue. Now we're going the left side, top and bottom.
Thanks for clarifying.
Yeah, you're welcome. My bad. What's the relationship between those two structures? They are different. They do not have the same molecular formula. One has 4 carbons, the other has, how do you spell different?
Oh, you did it right.
Fifth. That's how I spell it.
They're different. Okay, what happens between, actually if we did orange on the far right, up, down, different on our diagonals, also different. Oh man, let me color code that. Those should be blue, right? They're all different. Okay, what happens when we compare the bottom two? We have the same molecular formula. They are indeed they're not superimposable. So we're now in that isomers definition. Notice the isomers can split. Do we have the same atom connectivity? No. Okay. So what we can go through and do is take your straight chain, and what I'm going to do is take that last carbon. Okay, so we went through and numbered it. I've got 1, 2, 3, 4 carbons. 1, 2, 3, 4, same numbering. In our rightmost structure, where did I attach that last carbon? To carbon number. The rightmost structure, I attached that carbon to carbon number 1. Where is that carbon attached in the leftmost structure? Number 3. We do not have the same atom connectivity. We've changed the location of those atoms. So what we're now looking at are structural isomers. Okay? Chapter 5 goes through and branches out structural isomers and stereoisomers into a couple extra definitions, which we won't get into quite yet, but this flow chart is going to get squished and more lines are going to pop off the bottom of it, okay? As well as identical, actually. Questions about this? Okay. Yeah?
Is the pattern of aromatic CNH like the
You don't want to do that. Don't look at the aromatic patterns. No. Aromatic is too broad of a definition, which you'll learn in second semester. Questions about classifications on our molecules? Okay. So nomenclature. Now we actually want to be able to name these things. So you should have seen, or this slide should look familiar. This was our overall summary of everything. What we're going to focus on primarily within this chapter would be which section of our nomenclature? Our alkanes. We're looking ultimately at rule number 9. So we can, or priority number 9. We'll need to know all of the numbers of carbons and their Greek prefixes. Up to you, however you want to memorize that. Through 6, absolutely back of your hand, you should know that without any questions. 7 to 10, you will probably see a few questions on those. You just see them less frequently. Okay? So make sure you get those memorized. The next issue that we're going to run into, because we're only looking at alkanes with no other functional groups, is we're going to end up with branched structures. Okay, so instead of having something in a nice straight line, we've got carbons popping off every which direction. We need to come up with a consistent way to name these structures so that we come up with the exact same name for an individual compound, regardless of which way I've rotated the bonds. So if we think back to that previous example, where can I draw it? Draw one over here. We had our butane, like that in our lower left, the straight line, versus on the far right, that structure. Both of those need to reach the exact same name because they're identical. Right? So this is again where we come back to this idea that organic molecules do not have an up, a down, a left, or a right. We have to be aware that they are constantly flipping and moving. So when we go through to name, we have to come up with a consistent pattern to always approach this. So we move into our blue box. We're going to find the longest carbon chain that contains our highest priority group. In this case, since it's only alkanes, all we have to do is find our longest carbon chain. So we take a look at the structure on the left. We can start usually on the leftmost side. I would highlight my longest carbon chain. How many carbons are in that chain? 4, which means I'm looking at bute. We take a look at the other structure. How many carbons are in my longest chain? 4. I don't care that they're aimed different directions or it's even compressed in a smaller space. That's irrelevant. It's still 4 carbons. It's still bute. Is that a question? No? Next step of our rule is start numbering at the highest priority. Okay, well, do we have a highest priority in this? No, it's just a straight chain, so we can skip that. Okay, we can then go through and add the appropriate ending to the suffix to identify our functional group. What's our functional group? Alkanes. What's our ending for our alkanes? A and E. In both cases, we're looking at alkanes. We come up with butane. Use numbers to specify locations. Well, that's assuming that we have something else in our structure. Is there anything else in our structure? Nope, so we can skip that rule as well. So at our simplest level, we count our carbons, and we name our structure based on the number of carbons within it. Yes?
So the number identifying the location would be referring to which carbon?
Yep. Yep. In this example, in theory, hopefully everybody sees this as a relatively simple example. We will look at some more advanced ones. Okay. So before we do that, I do kind of want to break this down. Oh man, that color really didn't show up. The thing in quotes says cyclo, and the giant empty space in this name on our right also says cyclo. Oh yeah, it says shape and then cyclo down below. Okay, so what this is attempting to go through and do is break down a name, a super complex name, into what each of the individual pieces, where they are, what you would see in the name, and then what each of the names look like. Okay, so in the box, we would start with the number location. So we'd start off our structure by specifying where something was. We follow that with a dash specifying the amount of that substituent. Okay, followed by, oops, I definitely made a mistake, followed by the name of that substituent. We would continue to do that until we've named all of our substituents. So all of the pieces that are attached to our main structure get named first. We then follow that up with our next, it's shown as the next line, but it's all run together in one name, with the shape of our molecule, which is only really relevant for our cyclic structures. So to specify a cyclic structure, we just say it's cyclo. Right? If it's not a cyclic structure, do we need to say cyclo? No, it just disappears from our name. Followed by the number of carbons, so our Greek prefix, number of carbons. Our carbon hybridization, okay, which is ultimately referring to ane, ene, or eine, okay, followed by the number for our location for each of the functional groups that follow off of that. All right, I know that's a lot of different pieces to get thrown into that. But the idea is to color code each of these. So if we start with our leftmost structure, or a leftmost name, okay, how could we come up with a structure from this? Where should we start? What was your suggestion?
That is that 6
We want to start, I would probably argue, not even with the suffix, because that gives us an idea of the functional group, but it doesn't tell us our overall structure. We couldn't really draw anything with that, particularly if it's alkane. What do we draw? What's our alkane functional group? Carbons and hydrogens. That doesn't tell me how many carbons or hydrogens there are. That just says alkane. So where I would typically start is in with that green section, with that hex. What does that hex mean? I've got 6 carbons. Now I can jump to the suffix. The suffix says ane, which means those 6 carbons are all connected via single bonds. Okay? And remember, our very first rule when we went through to draw out come to our name was the longest carbon chain. So what I would now draw is 6 carbons, 1, 2, 3, 4, 5, I can count 6 carbons in a straight chain. What I've now named is the hexane portion of that name. That's it. Now I'd go back to my substituents. Okay, and I actually made a mistake with this, which I'll correct right here. Okay, we'll talk about that in a second as well. Okay, it says I have methyl substituents. What does my methyl look like? One carbon. Because we're looking at a substituent, it's connected to my main chain via a single bond, which means for a methyl, I also have 3 hydrogens. So I'm looking at a CH3. How many CH3s do I have? I've got, exactly right, 2 CH3s because it says so. Where are those 2 CH3s? They are connected to carbon number 3. Where is carbon number 3? Third one from the left. Wrong. It's the third one from the right. Does it matter? No, it doesn't. Okay. You can flip and rotate that structure. Okay. So it didn't matter which way we counted. How do we actually decide where carbon number 3 is? Well, it can be helpful to actually put down numbers. With a structure that's as small as we've got here, it's not that big of a deal. Okay. In future examples, it may be really, really important to specify those numbers so you know exactly where to put those atoms. Okay? And we now have our structure for 3,3-dimethyl hexane. Why did I write in 3,3? If we go back to our overall naming, it's the number of the location specifying our substituent. We have 2 substituents. So instead of saying 3-methyl hexane, I can condense that into being dimethyl, but then I must specify where each of those methyl groups are. That's why I need both 3s. So the number will only refer to a single substituent. If I have multiple substituents at the exact same position, I need to specify that position twice. Okay? How do we separate our numbers? With a comma. How do we separate our numbers from our letters? With a dash or a hyphen. Okay? This is one of the reasons why nomenclature is incredibly frustrating, particularly when it comes to sapling. Okay? What happens if you put in a space? It's wrong. Okay? This is how nomenclature works. There is one rule, you must follow that one rule. If you deviate from that rule in any respect, it is wrong. That is nomenclature. Okay? How do we kind of sneak around this? Okay? Number 1, look at your final exam. Final exam is composed of a standardized test, which is all multiple choice. Okay? You don't have to worry about random spaces being marked incorrectly because they give it to you. Okay? How can I get away from it in sapling? I don't ask any questions where it forces you to type it out and get all the spelling correct. I'll ask them as multiple choice questions. Okay? That said, there are a few questions that are where you have to write out the correct name, and probably will be extremely frustrating for you because you will put in a space in the wrong spot, you'll put in a dash in the wrong spot, or a comma in the wrong spot, and the whole thing flips out at you. Okay? There's only 1 or 2. Okay? Most of them are multiple choice. when trying to come up with the names. When it comes to drawing out the structure is going to be a tedious thing for you to deal with, regardless of whether it's in sapling or not. Within sapling, drawing out structures is always going to be a pain. All digital imaging is a pain. Guess what any organic chemist has to do when they want to present their results? They have to digitally image everything they do. Okay? So it is a useful skill to pick up on trying to use the interface that sapling has to go through and draw structures. If you get it wrong once and you are positive it is correct, do not click submit again, because it will still be wrong. Okay? If you're really positive that it's correct, delete everything, redraw. If it's still wrong, stop. Email me. Okay? And I will try and help you figure out what went wrong with what you've got drawn in there. Because at that point, it's probably something that you're missing. Either not in lecture, not in the material, something's wrong. So we got to get that fixed. Okay? Questions about that? Let's take a look at one more with our invisible cyclo in the middle there. Okay, because that last one I don't want to talk about because it's an alcohol, so we won't deal with that yet. Where do we start with our structure, with our last name? I would start again with the hex. Okay, this time I'd be a little bit more careful. Not only do I have to go after, but I'm also going to check in front. Okay, because if I go just after, I'm going to end up with the same straight chain of carbons. But if I look at the word in front, which I know you can't see, it says cyclo, which means those 6 carbons are arranged in a circle, as close as we can get 6 carbons to a circle. What shape is that? A hexagon. Hex for 6. So we could draw in our hexagon. What you'll find with the rest of this chapter is you're going to become either really good at drawing cyclohexanes or you're going to get really, really pissed off. Either way, you're going to have to draw a cyclohexane, so get used to it now. Now what do we do? Oh, I also did this name wrong too.
Number the carbon.
Might be a nice idea to number our carbons, particularly because if we look at the number I just quickly added into this, we want to identify position 1 and 3 for methyl groups. And we know our methyl is to be a CH3. The di means that I have 2 of them. I need to put them at position 1 and position 3. Well, where is position 1? Until we specify it, it is anywhere we want. So just to be weird, specify it at the bottom. We got our 6 carbons. Where do I put one of those methyl groups? On 1. Where do I put the other methyl group? At 3. There's my structure. Questions about that? Is it as easy as that? Not quite. For there to be a double bond, what does our suffix have to become? Our suffix would have to be -ine. So this is one of the big things I'm noticing a lot of people doing. Oh, it's a ring, so it's aromatic. No. For it to be aromatic, it actually has to satisfy a bunch of rules, but what you're actually considering is that it has a ring and 3 double bonds. Okay? That is your aromatic structure. At this point, this just says cyclohexane. There are no multiple bonds within this. Okay? Yes?
How come it's 1 and 3?
That's what the name was, sort of.
Can you,
I had to add the 1. Yeah, I had to draw in the 1.
could it be 3 and 5?
So what happens if we change that to be 3 and 5? So first off, it's going to be a little bit more challenging for me to deal with. Did we ever write it as 5, 3? No, what should we put front? Smallest number first. Okay, so if we wanted to change our structure, we could go and call it 1, or sorry, we're doing 3, 5. Next issue. When we deal with rings, our substituent first and foremost goes to what position? 1. Your very first substituent on a ring will always go to position 1. So if you were given the name 3, 5, is that an appropriate name for this structure? No, because while we may still be drawing the exact same structure, it's technically the wrong name because you used the wrong numbering system. So even though you were able to take the name and draw the exact same structure that anybody else would draw if it was named 1,3, you are still technically wrong. Okay? You want to use the smallest sequence of numbers possible. So the 3,5 doesn't work for us because I can better number that 1,3.
So do we write in the numbers?
No, the numbers would be given to you. You'd be given the name, or I'd give you the structure. Okay? So if you were given the structure, whoops, I don't want that.
It's always starting at 1, right?
That's what I was about to deal with. What would we name this structure?
1 and 2.
Okay. So it is still a cyclohexane. It's still a dimethyl, but where are our methyl groups? 1 and 2. Why did I number that direction? Why couldn't I have numbered 1, 2, 3, 4, 5, 6? I can absolutely number that way. And that would give me the name of the structure being 1,6-dimethyl cyclohexane. Is that name correct? No, because you used numbers that were too big. You need to use the smallest numbers possible. So 1,6, even though it's the exact same drawing, is wrong. All right? So nomenclature ultimately comes back to what is the rule, follow the rule. Don't follow the rule, you're wrong, period.
Can you repeat that again? Why?
The rule is you must use the smallest numbers to number out your substituents. That's your rule. It has to be the smallest number. 1,6, if we add those numbers up, gets us 7. If we numbered it the other way, 1, 2, we get a smaller sequence of numbers. So the 1, 2 is the better way to refer to this structure.
So if you had something that was like 1, 4, you don't have a choice because it's 3 units.
Yep, you don't have a choice. It would be 1, 4.
Maintain 3 units away.
Yep.
What if when trying to name it, like, you wanted to specifically say that you wanted to go that direction because for some reason it couldn't move double bonds or what have you?
So if there's other functional groups that force a higher priority, you always put the highest priority at the lowest number. So that can cause you to use larger numbers, but that's only because the larger priority is getting the smaller number. Okay? So we always want to use the smallest numbers possible for your highest priority groups. Okay? Sounds a bit obnoxious, I know. It's really not that bad if you really have the rules out in front of you and you just follow the rules. Okay? If you don't follow the rules, that's where it becomes problematic. Okay? When we looked at, just realized that I didn't mention this on the last slide. Let's clear everything. Said methyl here, and we went to a CH3. Why did I say methyl? Why not just meth?
Meth just means one.
Meth means 1 carbon. What does the YL add to this? The YL is referring to it as a substituent. That's all it means. So you will see that YL show up at the end of each of your substituents because we're referring to it being a substituent on our primary structure. Okay? And that, pretty sure, set up in that branch structure. Shortest branches are named with YL, and then we'll name our longest chain with the appropriate suffix. Or, is that suffix? That's a prefix. That one's a prefix. Those are suffixes. Okay? So let's take a look at a little bit more difficult example. What's the difference between the two structures shown here? It's just how they're highlighted. They are exactly the same structure. Okay? So if they're the exact same structure, we should get the exact same name. So the general tendency when you go through and try and highlight, okay, is remember, if we want to come up with a name, find the longest carbon chain possible. Okay? One first pass might be, well, I look at this, I see 4 carbons. Yes, those 4 carbons are all in a straight line. Is that the longest chain? No. It branches. At very least, I could add 1 carbon that way. What if I branched upwards? I could add 3 more carbons. Okay? So when you're given a structure, you're going to have these carbons going every which direction. You have to go through like a little maze to find the absolute longest possible chain. So if you look really carefully, probably at the PowerPoint slides, you'd see this a little bit better. In the leftmost, they highlighted this sequence of carbons. How many carbons is that? Holy crap. You guys counted fast. In our rightmost, they highlighted this section. How many carbons is that? Ooh, interesting. What do we do now? Would we get the exact same name?
Not necessarily, maybe, let's go on.
If we look at our pieces, are substituents all the same? No. So which chain do we use? We use the one on the right. Why do we use the one on the right? Actually, that might actually work, but that's not the rule that I've actually heard. We want the most number of substituents. Okay. So we want to split it up. So if we take a look at our leftmost structure, how many substituents do we have? We have 3. Rightmost? We have 4. Okay. If we looked at our rightmost one, what are our substituents? So this is how I would go through and name. I've got a methyl. Methyl. I know this gets a bit redundant, but this is how I do it. Methyl, and then ethyl. Why ethyl? There's only 2 carbons. And then my main chain was, we said 7 carbons, so I've got heptane, because we're looking at single bonds all the way through this. And then I could go through and deal with my numbering. Where am I going to start numbering, from the top or from the bottom? Bottom, because if we start from the top, most of our substituents have higher numbers. So we're going to start our numbering from the bottom of our heptane chain. 1, 2, 3, 4, 5, 6, 7. I'm glad I wrote those in the same color so you could see them. But you know we're numbering from the bottom up. I could then go back and add some extra information. I have a 2-methyl, 2-methyl, 5-methyl, and a 3-ethyl. Oh, how did I get 2?
Because it's next to
Oh, I see what I did. Okay, thank you. Make sure you watch what you're doing. Okay? We could then go through and put this name together. Okay? Ultimately, the reason why I won't show you how to put this name together at this point is because I'm kind of lazy, and if it's multiple choice, I now have enough pieces that I can figure out what my answer is. Okay? So what we're going to end up calling this is 3, 4, 5. Whoops, sorry. I got to get those numbers right. Let's try this again. 3-ethyl, 2, 4, 5, trimethyl heptane. Why did I put the ethyl first? Alphabetical order. Yeah, don't look at me. All right. So you have to organize your substituents based on alphabetical order. All right. So everybody happy with ethyl and methyl?
No.
Just identifying ethyl and methyl. We don't got to worry about the order.
Yeah.
All right. So now the question. Let's move to the blue structure. I know this is the wrong structure, but this is going to help segue into the next piece. Take a look at that bottommost substituent, which I'll highlight in red now. How do we name that substituent? There are 3 carbons, but that means 3 carbons in a straight line. Do we have 3 carbons in a straight line? No. How do we name that piece?
I'm sure you're about to inform us.
There are 2 approaches to naming that piece. We go through and we count it out as our longest chain within our substituent. Our longest chain in that substituent is 2 carbons, so it's an ethyl, but then it also has a methyl at position 1. So when we do our substituents, we will number where it attaches to our main chain. So what we've got in that case, I know this is confusing, but I'll give you a slightly easier version of this in a second. So there's our longest chain, 1, 2 carbons, so it's ethyl. We have a methyl substituent on our substituent, so we would have 1 methyl ethyl for that substituent. Okay, so let's write that one out. We would have 1 methyl ethyl. That's just the name of the substituent. Where is that substituent located? On a heptane. But if we write it out that way, that looks like we're saying methyl ethyl is on position 1. Is it on position 1? No. We got to drop parentheses around that to then say it's located at 3. I think 3 is going to be our shortest number. We would have 3, 1 methyl ethyl, heptane, and then we'd also have to address the other substituents, our other methyl groups in there.
It's 3.
What do you mean, how is it 3? Did I not count that right?
No, you're fine.
1 carbon, 2 carbons, 3rd carbon.
Wait, where?
I saw it was combined, so I got.
Here, let me point it out. Yeah. Here's our substituent. 1 carbon, 2 carbons, 3rd carbon, there's our ethyl, or our 1 methyl ethyl. Okay. If we numbered it the other direction, we'd end up with higher numbers. We have to go the shortest route. It's not ethyl methyl because the methyl is a substituent on our main chain substituent.
So this doesn't apply to ABC.
So ABC only refers to substituents on our main chain. What we just looked at here was a substituent on our substituent.
Okay.
Okay. Which you could then make another on another substituent. So it does add. Is there an easier way to reference this? Yes-ish. We could count the other chain. The other way we can reference that particular substituent is something known as isopropyl. Okay. So that name is a lot easier to remember, a lot shorter. Why is it isopropyl? Because the shape it gives is iso, and there's 3 carbons to make that shape, so it becomes isopropyl. What? Yeah, I agree. What you're looking at is what's known as common versus IUPAC. IUPAC goes through and identifies every single atom in all of their relative locations. The common name is where we go through and certain substituents carry very particular names. So with 1 carbon, we always hit methyl. There's no difference. 2 carbons, we always hit ethyl. There is no difference in naming. When we hit 3 carbons, we can now change our nomenclature system. If those 3 carbons are in a straight line off of our main chain, it's propyl. There's no way around that one. But what happens if we take one of those other carbons and we put it off of our main section? That gets us our 1-methyl ethyl or isopropyl. Okay. What happens if we go to 4 carbons? 4 carbons in a straight chain is going to be butyl. But if we move 1 carbon off, we can end up with our isobutyl. Where's that iso coming from? That's an eraser. It is this shape right there. That is your iso shape. We've added an extra carbon, so it's no longer isopropane, it's isobutane. If we put that carbon at a different position, we get sec-butyl. What does the sec refer to? Secondary. Take a look at that carbon where our substituent is attached. It's attached to 1, 2 other carbons. Sec-butyl. What happens with our last one? We get tert-butyl. Take a look at where it's attaching to your main chain. How many carbons are attached? 1, 2, 3. Tert for tertiary. 3 carbons attached to it. These are your common names. I would like to say you will never be tested on common names because that would be ideal. This is not the truth. You will almost be guaranteed to see these types of names show up, okay, which means you are still responsible for them. When it comes to any exam within this class, you are more than welcome to use IUPAC nomenclature if you want, or you can use the common names. You will probably start to use the common names because it's a heck of a lot easier to name these. Okay? Feel free to pack up. I'll go ahead and give you the IUPAC name for the tert-butyl as an example of why you probably don't want to deal with these.
Any good websites you go to practice these things?
There are tons of websites out there with nomenclature. You just got to find them. I don't know what it is. Tert-butyl is also known as 1,1-dimethyl ethyl. Okay. That's your nomenclature. We'll pick up there on Monday. Yes.